Welcome back, everybody. Let's go through a second example of a chi-square test for independence. In this particular example, we're going to be dealing with some real data that was published in the Journal of the American Medical Association. I usually try to use numbers in class that are relatively small and easy to work with, because then we're not stumbling over the mathematics. But this one has some real numbers, and it's an interesting example. Let's read through it. It says, based on the highly influential data reported in the Journal of the American Medical Association, determine if there's a relationship between hormone replacement therapy, which is for postmenopausal women, and coronary heart disease. We're going to test that with an alpha of 0.05. Let's just take a second and look at our actual data. This is our observed data, the data that was actually collected. And we have data for two different variables. Women, in this case over 16,000 of them, and they were all nurses taking part in this research study. They were all postmenopausal women. They were randomly assigned to one of two different groups, a group that received hormone replacement therapy or a control group. All of these women were suffering symptoms that hormone replacement therapy would help alleviate, things like hot flashes, for example. It's very common for women, once they become postmenopausal, to seek out hormone replacement therapy because the symptoms of menopause are often really negative. They're just hard to deal with. And in that respect, hormone replacement therapy is actually very effective. It's been known for a long time that women taking hormones later on in life increase their risk of certain cancers like breast cancer, but it was always thought that women taking hormones would lower their chances of heart disease. This study found the opposite. Let's just look at the numbers for a second and make sense of them. Let's figure out these percentages real quickly. Of the women taking hormones, how many of them developed heart disease? CHD in this example represents coronary heart disease. So there were 164 women who were diagnosed with heart disease, and that's out of the 8,506 who were randomly assigned to take hormones. And that comes out to be a pretty small number. And for this example, we're going to go out to 3 decimal places just because we need to be able to distinguish between the values. But I see 0.019, that would be 1.9% of the women taking hormones were diagnosed with heart disease. Let's compute the same percentage for the women in the control group. They were receiving a placebo. They were not receiving any additional hormones. So 122 of those women developed heart disease. Because remember, people as they age develop heart disease. It's a common thing. There were 8,102 of those women. So that came out to be about 1.5%. One thing that makes this example pretty interesting is the difference in the absolute values of those percentages seems really small. It's a difference of less than 0.5%. But now look at those frequencies. Let's just express that difference in another way. That's a difference between 42 women having heart disease. So it's a pretty big deal. Even small effects can have important, meaningful, lasting implications for people. I'm sure those 42 women wish they weren't in that category. So let's go ahead and start with step 1. Our null hypothesis, of course, would state that there's no relationship between these two variables, no relationship between hormone use and coronary heart disease. And if there is no relationship between these two categorical variables, then the chi-square value would equal 0. The alternative hypothesis, of course, is that there is a relationship between hormone use and heart disease. And if there is a relationship, the chi-square value, the chi-square statistic, would grow above 0. All right, let's figure out how much evidence we need to reject that null hypothesis. That's what step 2 is all about. And even though we measured 16,608 women in this study, remember the way that we compute degrees of freedom is simply based on the size of the table. And when you look at the table, we have 2 important rows and 2 important columns. So like our previous example, we have 2 rows minus 1 multiplied by 2 columns minus 1, which would be 1 times 1, which equals 1 degree of freedom. So if we have 1 degree of freedom, let's go ahead and look that up in our chi-square table. In this particular example, we're using an alpha of 0.05. We have 1 degree of freedom. So this right here is how much evidence we would need. we would need to find a chi-square value that exceeds 3.84 in order to say we have statistically significant results and these two variables are actually related. The reason why I picked 0.05 in this example is because an alpha of 0.05 is what was listed in this journal article. And I just want you to keep this in the back of your mind for a second. When we talk about medical research, we usually say that medical researchers need to use an alpha of 0.01. They need to have more evidence to reject the null hypothesis. And you can see in this case, if we used an alpha of 0.01, the critical value would actually be at 6.63. I want you to just keep that in your mind for right now. All right, let's go back to our data. All right, we were using an alpha of 0.05. We determined the critical value was 3.84. So here I have a chi-square distribution. We know it's a one-sided distribution because chi-square values can only be positive. And I marked off right here the critical value of 3.84. Okay, we know that step 2 is all about figuring out how much evidence we need, and step 3 is all about figuring out how much evidence we actually have. Well, here's our evidence right here. So let's mark off this table as our observed data, and then mark this table as our expected data. Keep in mind what these expected values represent. These are the values, the frequencies that we would expect if there's absolutely no relationship between hormone use and heart disease. In order to find these expected frequencies, we're going to use this formula right here. According to the formula, we'll take the frequency for an entire column, we'll multiply by the frequency for an entire row, and then divide by our sample size. So let's go ahead and get started. We often number these cells, 1, 2, 3, 4. We're just doing that for our benefit. If it doesn't help you, don't do it. It's no big deal. Here we'd have corresponding cells 1, 2, 3, and 4. So right now we're focusing on this table. Let's look at cell number 1. If I want to compute that expected frequency, I'll take the frequency for the entire column. Well, I'm in cell 1, so the entire column has a frequency of 286. I want to take that and I want to multiply by the frequency for the entire row. And again, I'm in cell number 1, so the frequency for this entire row is right here, 8,506. So that equals a really big number. I'm going to divide that by my sample size, which is 16,608 women. That equals 146.48 approximately. And because we're dealing with such large numbers here, and the numbers are kind of nasty, let's just do ourselves a favor in this example. We typically round to 2 decimal places. In this particular example, let's just round to 1 decimal place. So that would be an expected value, an expected frequency in there of 146.5. Let's move to cell number 2. Let's take the frequency for the entire column, 16,322, and then multiply that by the frequency for the entire row, 8,506. Let's then divide that by 16,608. That equals 8,359.5. So you can see where we're going with this. Let's just do one more. Let's look at this cell right here. The frequency for the entire column would be 286. We want to multiply that by the frequency for the entire row, 8,102. And then we want to divide by our sample size, 16,608 women. That would give us an expected frequency of 139.5. You can do that last one on your own. Let's just check to make sure things add up right. 146.5 plus 139.5 equals 286. And you'll see if you check, the other values add up appropriately as well. So we're feeling pretty confident about the expected values we just computed because they fit the table appropriately. They fit the table mathematically. Let's go ahead now and compute the chi-square statistic. Let's focus on this first set of cells right here. So this cell right here and its corresponding cell right here. Remember, in order to compute this chi-square statistic, we're going to have to sum up a series of fractions. And in the numerator of each fraction, we're going to take the observed frequency, in this case 164, subtract the expected frequency, 146.5, eventually square that difference, and then divide by the expected frequency. So in the first example, we've got 164 minus 146.5. We will square that difference and divide by 146.5. We need to do that for every set of corresponding cells. So We usually go on to cell 2 at that point. I can see that I went on to cell 3 right away. It doesn't matter what order you use. So let's just look at cell 3 for a second. This is labeled cell 3. This one here is labeled cell 3 as well. So in this particular fraction, I'm taking 122. I'm subtracting the corresponding value in cell 3 over here, 139.5. Eventually, we need to square that difference and then divide by the expected value of 139.5. Let's move on back to those corresponding cells that were labeled 2. Again, we start with our observed value, 8,342, which is right here. We're going to subtract the expected value, 8,359.5. That's right here. Eventually, we will compute that difference and square it, and then we will divide by that expected value, that expected frequency of 8,359.5. And then we have one more set of corresponding cells. We labeled those cell number 4. 7,980 minus 7,962.5. Eventually, we'll square that difference and divide by that expected frequency, 7,962.5. So it's a mouthful to say, it's a lot to write, we're dealing with real data, but it's just as easy as the other examples we've looked at. Once we have these fractions created, we can just do the math. No problem, we've got calculators. And remember, we should see a trend emerge. All of those numerators should come out to the same value. That's going to happen every time we have a 2x2 table. So let's go ahead and take these fractions and just reduce them a little bit. Let's figure out what's going on in the numerator. So in that first one, I would take 164 and then subtract 146.5. That equals 17.5, which eventually we're going to have to square. Let's move on to that next one. That next one's right here. So we need 122. We're going to subtract 139.5. You can see that equals negative 17.5. We're going to need to square that eventually and then divide by 139.5. And you can see we have those same similar numerators in these other fractions. Of course, every time we square a positive value, we get a positive value for our answer. But every time we square a negative value, we also get a positive value for our answer. So all of these numerators are going to turn out to be the same value. Let's just crunch out each fraction and figure out what these values are, then we'll add them up. So we'll start with that first fraction. We'll take 17.5 and let's go ahead and square it. I'm just going to leave that value in my calculator and then divide by 146.5. So that equals about 2.09, and we get that value right here. Let's go ahead and look at that second fraction. We have negative 17.5, so I'll go ahead and make it negative. We're going to square it, so it's going to turn into a positive value, and then divide by 139.5. So that fraction equals about 2.20. I'm back to rounding to 2 decimal places. Let's check out that third fraction that we have. 17.5. I'll go ahead and make it negative. I'm going to square that and then divide by 8,359.5. So that equals a pretty small number, 0.04. Let's move on to that fourth fraction, 17.5. We need to square it and then divide by 7,962.5. That equals another pretty small number, rounds out to about 0.04. Let's add them all up. 2.09 plus 2.2 plus 0.04 plus 0.04 equals 4.37. All right, so that is our obtained chi-square value. So based on all of our data, that's how much evidence we have. It's reduced to a chi-square value of 4.37. Let's see if that's enough evidence to reject our null hypothesis. We need to determine if this value is inside our critical region. Our critical region is marked off with a chi-square value of 3.84. 4.37 clearly exceeds that. We are indeed inside this small critical region. Critical regions, of course, are known as rejection zones, so we're going to end up rejecting the null hypothesis. Let's just start with our simple questions. Are we inside the rejection zone? Yes. All of the follow-up questions should have that same response. Follow-up question number 1, should we reject the null hypothesis? Yes, we should. So go ahead and X that out and then check off the alternative. We're going to embrace that. We're going to embrace that chi-square is greater than 0, which means hormone use and heart disease are indeed related in the population. Second follow-up question, do we have statistically significant results? Yes, this relationship that we're seeing is statistically significant at the 0.05 level. Next follow-up question, is it possible that we're making a type 1 error? Yes, every time we reject the null hypothesis, there is at least some possibility that we're making a type 1 error. And in this case, the probability over the long run of making a type 1 error in this type of situation is 5% because we used an alpha of 0.05. Let's go ahead and take everything that we just said and then make it more formal, interpret our results more formally in step 4. So we might say something like this. Our chi-square value is 4.37, and we found that it's inside the critical region. This is very unlikely if the null hypothesis is true, and that's why we reject the null hypothesis. In other words, our data is inconsistent with the null hypothesis, and that's why we rejected it. That tells us that we have a significant relationship between heart disease and hormone use. And remember, we computed these percentages, so we know the direction of that relationship. Hormone users are more likely to develop heart disease than people who are control subjects in the study. Let's write it up as it would appear in a journal article. We did a chi-square test with 1 degree of freedom. Our sample size was equal to 16,608 participants, and the chi-square value that we computed was equal to 4.37. Because that value was in this small little region, we can say the probability of finding that value just by chance is less than 5%. It's statistically significant. Remember I mentioned to you that most medical research uses an alpha of 0.01 to determine if it's statistically significant? Let's go back to that table real fast and just remind ourselves. If we used an alpha of 0.01 with 1 degree of freedom, the critical value would actually be 6.63. Let's go back and check our data. So let's just play the little game for a second. Let's say that we marked off our critical region at 6.63. Would we then have statistically significant results? Well, you can see our obtained chi-square value, 4.37, would not exceed that critical value. It would not be in the rejection zone. We would not have statistically significant results. So one thing that makes this particular example interesting is that the researchers found statistically significant results at the 0.05 level, but their results were not statistically significant at the 0.01 level. And sometimes journal editors, they provide a little bit of leeway. They thought that the results were so important that they were willing to give the researchers a little bit of slack and publish these results based on an alpha of 0.05. Remember when we first started talking about this example and we looked at the difference between these percentages and we noted how small that difference is? There's a difference of less than 0.5% in the rates of heart disease between the hormone users and the people in the control group. So if that's a relatively small difference, we're probably expecting a relatively small effect size. Let's go ahead and compute phi squared. You can see our formula for phi squared right there. We're going to take our obtained chi-square value, 4.37, and we're going to divide that by our sample size, which is a big number, 16,608. And the answer is actually such a small value that this particular calculator won't even display it in terms of a typical decimal point notation. It's displaying my answer to the -4 power. What that means is I need to move my decimal place 4 places over to the left. Long story short, it's going to look like this, 0.00026. So we don't need to wrestle with that incredibly small number. Let's just see that as less than 1%. That's a really small effect size. Less than 1% of the variability in heart disease can be explained by hormone use. In other words, a very small percentage of the variability in heart disease can be explained by that predictor variable, hormone use. I hope you found that example interesting. Example 3 is really interesting as well, and I'd like you to take this opportunity to work that one out on your own. You can compare your work with mine that's already computed, and of course, if you have any questions, just let me know. We'll end with some chi-square trivia. We've mentioned several times that when we compute chi-square, we end up squaring the numerator in each one of those fractions. So chi-square values are always going to be positive. Just keep that in mind. Here's something else that's pretty interesting. Chi-square values are very much like z-scores, and I can demonstrate that to you by looking at some critical values. You probably remember back from when we were doing z-tests that when we use an alpha of 0.05, the critical regions were marked off at positive and negative 1.96. We went through so many examples like that you probably have some memory of that. Well, z squared actually equals chi-squared. So if I take that value of 1.96 and I square it, I get a value of 3.84. Why is that important? Take a look right over here. If we use an alpha of 0.05 and 1 degree of freedom, where's the critical value? 3.84. So chi-square values and z-scores are very closely related. Now we've learned altogether many different tests. We've learned a basic one-sample z-test. We learned a one-sample t-test, an independent samples t-test, a related samples t-test. We learned analysis of variance. We learned correlation. We learned regression. We learned chi-square. What we're going to do in the next video, in the next chapter, is talk about how to choose the most appropriate test. I'll see you in the next video.